Okay, let's kick things off. So today we are going to be doing the first chapter of Decision Maths 1. So we are roughly following the Edexcel A-level Decision Maths. Okay, so if you want to, there are textbooks, you can find them online that will follow basically with what's happening alongside this. I figured that was the best place to learn how to try and pass these exams. Grew up doing Edexcel maths, really like some of the books, found easy to teach myself. Yeah, it's been really nice reading their textbook, to be fair. It's like a purple textbook with a like graphical satellite on it. It's really nice. So I've been following along with that. So this will roughly follow that book with some of my own spin on it, basically. That's the vibe. Okay, so chapter 1 is algorithms. So algorithms are basically a set of instructions that tell you how to do something. And my favorite one of this when we did in undergraduate was in computer maths, computing for mathematics. It was the classic problem of like, get everyone to write out how you like make a cup of tea. So, you know, you might say, go get a mug and pour boiling water into it with a tea bag. Or you might say like, put some milk in the cup and then put boiling water in, then put the tea bag in, or whatever order you decide to make a cup of tea. I think people have strong opinions about the right or wrong one. And the point being that when you actually follow through these instructions, if you had never ever made a cup of tea before in your life and you didn't even know what a cup of tea was, let alone like all of the components that go into it or the typical way that people make them, if the instructions aren't clear enough and aren't explicit enough and aren't unique enough, if there's like multiple different ways of doing something, but you actually really need someone to do the first one, using a bad algorithm, but basically when we talk colloquially, that sometimes use a bad algorithm. So it is using something really familiar like making a cup of tea was a really nice way to sort of show people like when you write out instructions, and this is true for maths and proofs as well, like you have to be clear, concise, and unique in what you're saying so that there isn't sort of ambiguity. What is the symbol? So this thing, it sort of just means chapter. I don't know. It's something that I've always written out from undergrad, is like circle with like that. Don't know what that line is. It's the section symbol. Okay. Yeah, I think one of my my geometry lecturer in first year of undergrad used it, and I just really like it. Let's have a little history lesson on that then. Section symbol. Also known as a silk row, is a typographic mark used to cite individual sections of legal codes and statutes. You can type it quickly on Windows using Alt-0167, apparently. Where does it come from? Section symbol, section mark, double S, or silk row. Origin. Ligature formed by the combination of two S glyphs, which is, yeah, how I write them. Others have theorized it's an adaptation of the Greek paragraphos, a catch-all term for a class of punctuation marks used by scribes with diverse shapes and intended uses. In The Sims, it represents currency. I love that. Okay. Learn something new every day. So yeah, they're basically just section 1, chapter 1. I'm going to use them for lectures. So like every stream is going to have a new section symbol. So an algorithm is a collection or instructions outlining a procedure. And then in the way they teach it in Edexcel, they can also be flowcharts. So my main interaction with flowcharts is nothing super mathematical. It's when there's a really nice pop maths magazine called Chalk Dust, and in Chalk Dust there's always a like which equation are you, and then you follow the flowchart and you answer a series of yes or no questions. It's like, do you prefer pure maths? And it's like yes, and then you follow through. And so that's a flowchart. Basically, it's like you do whatever it says in the box, or you respond to whatever it says in the box. It's maybe yes or no, or maybe it's like, you know, which category do you fall into, and then you go to the next step. So that's also a way to algorithm. A good algorithm is, and then this is from the book itself, it is precise, clear, and will terminate. So what you don't want is an algorithm or a set of instructions that has no exit or break point. Not only is that, like, if you're talking about programming something like with a computer, it'll just go forever, which is bad, expensive, and a waste of time. But also it doesn't actually get you to the end result. Like if you were describing how to make a cup of tea to someone and you were like, oh, boil the kettle. And then if the water isn't currently boiling, boil the kettle. And you would get stuck in this loop of like, well, if you weren't paying attention or whatever, and you would just forever pressing boiling the kettle and never moving on to the next step, you wouldn't get a cup of tea out of that. So having a really clear sort of exit point, or maybe a better example in that case might be, you know, if there are no tea bags, what do you do? Or having alternate routes around. I'm just going to change the music that's playing because it is distracting me for some reason. Cool. So, the example from the book, which I quite like. Hey, Ashley, we are doing decision maths. Exciting. Talking about algorithms. There are some really good videos actually online of teachers getting their students to be like, tell me how to make a peanut butter and jelly sandwich, and then like the absolute chaos that ensues from doing it wrong. Very entertaining. Have I made a decision? No. Don't be ridiculous. I wouldn't do such a thing, but I will know how to by the end of this, I'm sure. Maybe. Okay, so example 1. Write down any integer. Integers being whole numbers. Square. And then sum its digits. Repeat until the answer is 1, which will make it a happy number, or until you loop. And this is unhappy. Okay. You got an integer tattoo recently. Ooh, tell me more. Tell me more. That's really cool. I like a good maths tattoo. I think it's a very, very fun way to celebrate nerdy culture. Maths tattoos, yes, please. Yeah. Yeah, they're pretty cool. It's pretty cool. Okay, so things to know about this algorithm. It does imply an endpoint. Well, it implies that either it will always get to 1 or it loops. Those are the only two options. I'm assuming that there is never a case where it won't do one of those two things. Otherwise, we would end up with this infinite loop. But we can try it and see what happens. Is a good way to go about this. So let's start with the number. Pick a number. One. Okay. Oh, let's go for a darker color than that. 1 and 2. Okay, y'all are really pushing the boat out here. So if we start with 1, write down any integer, square, then sum its digits. So 1 will go to 1 squared, which is equals to 1. We sum the squares, and that's good. Repeat until the answer is 1. It's 1. So it's a happy number. There's a formal way to do this, but we're going to ignore it for the minute. Okay. What was... Okay, actually, that has vowels in it. No, it has Y's in it, which is vowel in Welsh, but still. 23. There we go. Okay, so 23 goes... So we do 2 squared and 3 squared. So square, then sum. So square the digits, then sum them. And a t. That's just not a number. It's definitely not an integer. Okay, 2 squared is 4, plus 3 squared is 9, so we get 13, which goes to 1 squared plus 3 squared, which goes to 10, which goes to 1 squared plus 0 squared, which goes to 1. Okay, we're happy again. You've written 3 cubed. I have written 3 cubed. You're so right. Okay. Let's pick another number. One more just to see if we can get something to go. 7691. Okay. I'm getting a calculator for this. 7 squared plus 6 squared plus 9 squared plus 1 squared is 49 plus 36 plus 81 plus 1, which is... Negative number isn't a bad idea. That's true. 8 squared, 6 squared plus 9 squared plus 1, which is 167. 167 is going to go to 1 squared plus 6 squared plus 7 squared, which is going to be 1 squared plus 6 squared plus 7 squared, 86. 8 squared plus 6 squared is going to go to 100. And then 1 squared plus 0 squared plus 0 squared is going to go to 1. Does anyone know any unhappy numbers? So far, we're getting pretty happy. Let's do... $11. 11 goes to 1 squared plus 1 squared, which goes to 2. 2 goes to 2 squared, which goes to 4. 4 squared goes to 16. 1 squared plus 6 squared is 37. 3 squared plus 7 squared is big enough I can't do it off the top of my head. It's 58. 5 squared plus 8 squared. 25. 64 is 89. 8 squared plus 9 squared is 145. This is going on for a while. I'll give you that one. 1 squared plus 4 squared plus 5 squared. It's 42. 4 squared plus 2 squared is 20. 2 squared plus 0 squared is 4. We've looped. Ugh. Unhappy. Ooh, that was a long one. Okay. So it does say choose an integer, but if we were to choose a negative integer, because we're taking the digits of the number is never going to be positive. So if we took like minus 77, for example, the digits of that would be 7 squared plus 7 squared. So it's the same starting with plus 77. So negative numbers, not too bad. You expect most numbers are unhappy. You have to go via power of 10. So, I mean, we started with it doing it 3 times. 123 and 7691, and we got happy quite quickly, which is impressive. Ashley's claiming that the conjecture is multiples of 11. But there's something interesting about this where we can look at, say we started with 4, right? If we started with 4, we'd go to 4 squared, which would take us to 16. So we'd just jump into this algorithm here. So it doesn't have to be a multiple of 11. I think it's something around, I don't actually know this, but I just thought it was a really nice problem. I think it's something around powers of 2. So if you hit any of the powers of 2, I think it comes back down. But given that it's told us that this is a happy algorithm and these are called happy numbers, I'm going to guess they're actually a thing. So we can check that out. Happy numbers. Eventually reaches 1 when it's replaced by the sum of the square of each digit. Is this an open problem? Natural density of happy numbers. Yeah, there's nothing. 4 is a power of 2. Yeah. So I think if you go through those, it doesn't seem to like. Origin of happy numbers is not clear. Happy numbers were brought to the attention of Reginald Allenby by his daughter, who learned them at school. They may have originated in Russia. Excellent naming. Made the conjecture just because you did 11 and someone else said 77. Yeah. Interesting. But it was a nice algorithm. Also, hi Cap, Wiz. I hope you're doing well. Okay. But seemingly, those are the 2 options. I'm guessing the way that this is constructed and the fact that just quickly looking at happy numbers and happy algorithms is sort of established that numbers will always loop or reach 1. Who knows? So that's just an example of an algorithm. but we can write it out more formally. 32 is a happy power of... Is it? Oh yeah, wait, we did 32, didn't we? No, we did 23, which would be the same as 32. Ah, that's fun. So reversible numbers and scrambled numbers. Like if 7691 is happy, then so is 6971 and 1769 and, you know, all of the possible combinations of them. This is not what this lecture's about, but that is really... One of my friends shaved his head recently, and he was saying that he felt like he looked a lot rougher than he was now. And I told him, because he's really into musical theatre, that he looked like 24601. 11, 101, 110, also all equivalent. Yeah, that's really fun. Okay, so let's look at how we would write out sort of a more formal algorithm. So consider the algorithm below. So more often than not, so we have like the step that we're in, n equals 1, a equals 1, and b equals 1. Step 2, print a and b. Step 3, let this new number c be a plus b. Step 4, let n is n plus 1. Set a to be b and b to be c. 5, if n is less than 5, go to step 3. And then 6, if n equals 5, stop. Okay, so this is a much more like classic algorithm, and when I think algorithms, I think this is what I think, which is essentially a way of writing things that starts looking really similar to pseudocode. So it almost feels very like programming language-esque, and pseudocode, I think, is just writing code out, but like sort of not using a specific language. It's do the steps, write the algorithm, without actually programming it or putting it into a specific language. So you might use sort of colloquial, you might use like less formal terms for it. An informal plain English description of an algorithm or computer program. So it's just a much more like natural way to write this. Now this is pretty programmable. Like we could code this up quite nicely. But what it's saying is we have variables. So we have things that hold some value, hold some significance, n, a, and b. Interestingly, it does do sort of programming convention of having the lowercase letter, either n or I, be sort of our index or our number, you know, what step we're on. That's going to be our counter. And then the values that you're interested in are a and b. Print here means like write them out. So if we were going to put this into a computer, print would be literally just display on the screen. Like this is the bit, you know, do all of the hard out maths behind the scenes and then just tell me a and b. And then we introduce this fourth variable, c, to keep track of the sum and then basically shift everything along. So doing this algorithm by hand would involve looking at, and then this is where they like having tables. So I'm going to start a new page, I think. We're going to keep track of what step we're on. So those indices that we had before here. We're going to keep track of those, and then we're going to keep track of all of our variables, N, A, B, and C. And then we're also going to have like a print section, so like a display of what we're outputting. So from the initial setup, we had step 1, we set N is 1, A is 1, and B is 1. Have a great weekend too. See you later. We're going to print A and B for step 2. So step 2 is, I can just do it here. Print A and B. So A is 1 and B is 1. So we take the value from the box A and put it in print. Same with B. Step 3 was let C now be the sum of A and B. So we can take A and B, which is 1 plus 1. So C is going to be 2. 4, we're going to add 1 to N. So N becomes 2. A takes the value that B had. So B had 1 from up here. So A goes to 1. And then B takes the value that C now has. 2. So I missed a step. So 5 here. N is not greater than 5. So we're just going to go back to step 3. So going back to step 3, we take C to be the sum of A and B. So we get 3. We take 1 plus 2. Step 4 is then add 1 to N. A becomes B and B becomes C. 5 is going to be looking at N. N is less than 5, so we're going to go to step 3. So step 3, C adds up A and B, so C becomes 5. 4, add 1 to N. Take B, put it where A is. Or let A become B, let B become C. Interesting that it only prints once. Yeah, I think that's an error on my end. But I was going to finish and then talk about that. So 5, go to step 3 again. 3, sum up those, you get 8. 4, add 1 to N. 5, 5, 8. And then 5. It is now N is equal to 5. So we continue. We do nothing, basically. So here, if N is less than 5, go to step 3. But if N is greater than 5 or equal to 5, we don't do nothing. Banana!
Ring, 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 ring. Banana phone.
Hi, bestie. Yeah, I'm finally doing it. Already making mistakes. It's very exciting. Okay, and then finally get 6. N is equals to 5, so we stop. Okay, so I think what we should have been doing is, this is where I come through with my red pen. In here, there should have been a print C option, at which point we would have had 2, 3, 5, 8. assuming that that did happen, the printed outputs so while this algorithm, if this was being done on a computer, the computer would be running, and the thing that we saw would be 1, 1, 2, 3, 5, 8. And then it stopped. But if it kept going, it would have then been 13, something else, something else, something else, and it would have kept going. Because what this algorithm is doing is printing out the Fibonacci numbers. Or this one is finding the Fibonacci numbers, but if it was out printing things out, it would be printing out the Fibonacci numbers. So the algorithm so the Fibonacci sequence is a sequence of numbers where each next number is the sum of the previous two. So the Fibonacci numbers, we can write Fn. So the nth Fibonacci number is Fn minus 1 add Fn minus 2. And it starts from 1, 1. So 1 add 1, 1, 2, 3, 5, 8, 13, 21, and so on and so on. And each one of these is just the sum of the previous two, which is precisely what that algorithm was doing. It was sort of, summing two numbers and then shifting them along, which is quite cool. It seems to be looking at how they teach algorithms in school, that like the writing out of this algorithm, or like computing this algorithm in this really like table structure is how it's done. Maybe it's different now than when I was in school and we didn't have computer exams. But if you were going to like program this, you would be only checking the things that are printing, whereas this is sort of showing all of the workings behind the scenes, which is quite cool. I think that's like a nice way of doing things. Okay. So then they had an exercise. Use the algorithm to determine multiplication. Which this I thought this was kind of neat personally. So the algorithm is make a table with 2 columns, A, B. In the next rows, the left-hand side, so the left column, all of A, ignoring remainders. And in the right-hand column, double B. Step 3 then is repeat 2 until until the left-hand side is equals to 1. Don't call me a physicist. It's not very good. Thank you for the raid. Welcome in. I hope you had a good stream. We are learning decision maths. And by that I mean I learned decision maths and now I'm trying to teach it. We're doing all right. Step 4. Delete all rows. Where the left-hand side is even. And then step 5, sum all of the non-deleted right-hand side entries. When I first saw this, I'm going to be honest, I didn't think it was going to work. Didn't see this before, didn't really think about it too hard. And I was like, oh, that seems like a really weird way of doing multiplication. But actually, it is quite good. So if we actually go through that algorithmically, we need to make a table. So we have our value A and we have our value B. So let's say we want to multiply big numbers together, right? We don't want to do it sort of with smaller numbers. So let's do something interesting. So let's do 244 times by 125 is the example that they had. So we set A as 244 and we set B as 125. Could do it the other way around, doesn't really matter. So each time we go down in the row, we fill it out, we halve A and we double B. So half of 244 is 122, and then double 125 is going to be 250. Oh my God, so many raids. Y'all just like Simon shouted at me. How good. Thank you so much for the raid. Welcome in. How was your stream? How are you doing? Never heard of decision maths before. Briefly, what is it about? So decision maths seems to be the sort of algorithms, graphs, game theory side of maths. So very much like decisions or optimizing routes or travel problems or distances. It's the precursor to like optimization as a subject. Seems to be the case. The reason that we are doing it is because in Wales, when I was sitting my A-level exams, decision maths wasn't an option. So it was up to the school what modules you took. And most places offered either, so you had your core bit of maths, the like pure maths, the calculus that you needed to do. And then you had statistics, mechanics. And then in England, you had decision maths as a third option. You sort of had stats, mechanics, decision maths. Wales, we just had stats or mechanics. So going to university and doing, starting my degree, I never took the decision maths style modules because I didn't really realize, I thought they just like threw them in. And I'm now realizing like, oh, actually a lot of people actually had, precursor training. But yeah, so this is content that is or was taught to 16 to 18-year-olds that were taking maths syllabuses. At the minute, we're doing algorithms. Next, we're going to be doing graphs and networks, and then it looks like algorithms on graphs, and then it builds up to like the traveling salesman problem and game theory and prisoner's dilemma stuff. And yeah, the bit we're going to get to today is like sorting algorithms, which was the thing that really threw me during the streaming anniversary. So that's what we're doing. I'm going to learn it. I'm not, we think it's now taught in Wales. It was just very much not. Yeah, when I was younger. Quite a bit in common with operational research. Yeah, which is a connection that I've only like literally just now made when we looked at the D2 syllabus and it had like game theory and a lot of words that like I recognize from my friends sitting modules in operational research and like optimization problems. Had to choose between pure mechanics. Never heard of decision maths, but it was 30 plus years ago. Oh, wow. See, I think it sits in as a subset of pure maths. I think if I had to like really harshly draw the dividing, like maybe the more like the pure side of statistics seems to be where operational researchy people fall. But not every institution offers it as a subject. Yeah, because actually, there is a master's course you can do in the UK. So you can do an integrated master's, so a 4-year master's degree. So include is your undergraduate degree. And you either sit at what's called an MMath, so Master of Mathematics, or you can sit what's called the MORS, which is Master of Operational Research and Statistics. And I think a lot of this falls under that course. Now, when I had my undergrad in Cardiff, that was all part of the maths department. I think here at Warwick, it's the stats team that do maths, operational research, and statistics. I might be wrong on that, and I am going to go find out. We're past the point where we can assert things in education the way they were when we did it. Maths has been refreshed twice since I did it. Nice. Yeah. I think the book that I'm learning this from, so this content is following along. I'm teaching myself the Pearson EdXL 2017 book on decision maths. I think it's the 2017 one. I will double check. When was this written? Yeah, 2017. So this was written after my exams anyway. I did my A-levels in 2015. We had to do pure and then choose between mechanics and stat. Ah, yeah, that's more common. So my college did a similar thing where if you were just doing maths, so I did further maths, so I did both. But if you were just doing maths, you either did mechanics or you did stats, and it was one or the other. Some places used to do it where you did, 1 second. Let's have a little segue. A-level modules, circa 2015. For me, so there was core, 1, 2, 3, 4. Everyone had to do that. No matter what course you were on, no matter if you were further maths, double maths, whatever, you had to do C1 through C4. Then you had further pure. And you had further pure 1, 2, or 3. Now 3 was not offered where I was. That it's not a thing. And in most places, I think it typically isn't a thing unless they're doing a lot of support for quite high entry, like Oxbridge entry exam problems. Statistics, then, you could do 1, 2, 3, 4. I think there was a stats 4. Mechanics, you could definitely do. So again, my uni offered, so not at my place. My college offered 1, 2, and 3 in mechanics, but there was also 4 and 5. Stats goes up to like 6 or 7. Okay. So none of those were offered in my course, all the ones in bubbles. No. So for a A-level module, you had to do C1 through 4 plus 2 more. And each one of these was like a big exam. And then further additional 6 modules. And this is obviously, this was back when you sat your AS level as well. So your AS maths was like core 1, core 2, core 3. I think that was requirement for the half year A level. And then people sat like S1. Yeah, I think people typically sat that in their first year, and then in second year they would sit 4 and then either their stats or their mechanics modules. When I did my ASs, because I was doing further maths, I had to do basically all of these modules. So I sat C1 through C3, and in my first year I sat S1, S2, S3. And then in second year, which I hated this way around because I was always better at mechanics than statistics, but they gave me statistics modules. Like stats 3 was really hard in my first year. And then in second year, I had 4, 1, 2, and then 1, 2, 3. The other class to me, because there were a lot of us doing further in my college was like a really big place. They did it the other way. So they did mechanics in their first year and then stats in their second year. But we all did core 1, 2, 3, and then 4, FP1, FP2. I don't necessarily think it was the best way to do it, because a lot of the times, like, the harder stats modules or the harder mechanics modules sort of pulled from C3, which was, you know, at the end of the year for me. But this is now all nonsense. So I believe how they do it now is you sit 4 exams. That's the old days. In the modern days, in the modern era, it seems to be Pure 1, Pure 2, Applied 1, Applied 2. Where Applied is stats and mechanics. So they're like, you can't get away with just doing one or the other. You sort of have to do both inside of one exam paper. So, and then further maths, I'm not sure about that one. Where are the children? Any? I mean, they should be in school. AC maths. AS and A level. Spec. Further maths. Spec. From Land of Pumpkins, West Mission. Sorry, phrasing. Hey, from Land of Pumpkins, West Mission. Call me Pretzo. Hello, welcome in. We are currently trying to understand how maths exams work for 16 to 18-year-olds in the UK at the minute. Yeah, so this is true for A-level maths in the WJEC, which is the Welsh exam board. Just had 2 exams, one for pure and one for mechanics. Got 30 mechanics. Nice on the pure exam. Well done. Spec for further maths seems to be 3 modules in first year, 3 modules in second year. Further pure, further stats, further mechanics, further maths, further stats, further mechanics. So like 2 of each. Interesting. Okay. Back to the algorithm that we were looking at. So we have, as a quick refresher, you halve the left-hand side and you double the right-hand side. And then we're going to do something complicated in a minute. So half of 122 is 50, 11, so that's 61. And then doubling 250 goes to 500, which is nice. Halving 61 goes to 30.5, but we ignore remainders, so we just go to 30. And then doubling goes to 1,000. 30 goes to 15, which goes to, and this goes to 2,000. Half of 15 is 7.5, again ignoring remainders, so we just go to 7. This becomes 4,000. Half of 7 is 3.5, but again, ignore remainders, so we just go to 3. This becomes 8,000. Half of 3 is 1.5, ignore the 0.5, goes to 1, 16,000. Okay, so that's filled out the table, which is step 2. So we hit 3, repeat until the left-hand side is equal to 1. So that's done. Now we need to do step 4, so delete all of the rows where the left-hand side is even. So left-hand side is even. 122 is an even number, so we can cross that one out. 61 is odd, 30 is even, 15 is odd, 7 is odd, 3 is odd, and 1 is odd. So what we're left with is where we then have to sum the right-hand column. So I've lost my pen because my pen is in white for some reason. There we go. So this equation, 244 times 125, is equals to 500, add 2,000, add 4,000, add 8,000. This is a big number, add 16,000, which is, oh god, 0, 0, 5, 10, 10. So is equals to 30,500. And we can just check that directly. So 244 times 125 is in fact 30,500. Cool. So we didn't write out the steps that we were doing for that, but procedurally we completed the table until we hit 1 on the left-hand side, deleted the entries, and then summed. So that follows through the algorithm. So yeah, basically just summarizing, algorithms are sets of instructions that we need to follow. So we are just going to take a very quick ad break because I can see that it's coming up in a minute. So I will put you on a BRB screen for like 5 minutes. Don't go anywhere or go away. Go get some water, stretch, look after yourselves, and I will see y'all shortly. I don't have a proper button for that. Very upsetting. Okay, see you soon. Bye. Hello, welcome back. Is everyone with me? Oh, God. What is happening? Well, that's uncomfortable. There we go. We're back. I'm here. It's all good. So we had a few examples of algorithms to just whet the appetite a little bit. And then we had a massive segue about exams, modules, all sorts of unrelated topics. But it is now time for the thing that confused the shit out of me when we were doing the Streamiversary, which is the bubble sort algorithm. Bubble sort algorithm. This is where I make back the credit that I am a real mathematician, I promise. I have my qualifications, I know what I'm doing. So I have watched those videos online of the algorithms and like, you know, there's a line of unordered like heighted columns and they're all moving and then eventually they get in order, or like it's two different algorithms, sorting algorithms racing each other. So you'd have like two different ways and it looks kind of random and then they'd all be in line and it would like beep and then have the like and it's I can't describe the brain scratch that is. It's iconic. Thanos, that's not in Pearson Excel. Is that just delete half of the things until they're in a sorted list? But the reason that those things I think are so satisfying is because there's like 3 different things happening with those videos. Firstly, they add the pitch, the corresponding pitch to the thing that's being sorted. So like the tallest column is like a really high pitched beep and the smallest one is a really low pitched beep, or the other way around, I can't remember. So when it's like comparing two things, it like plays the note as well as looks at the height of the thing, and it also lights up the column. So you've got like the visual aid of the things being lit up that it's comparing, and then you've got the like the doot doot, and you can hear it as well, which is really, really cool. And did not help at all in me figuring out what the algorithms were, but now that I understand them and I've read it, it's nice to see and be like, oh yeah, that's what that's doing. I get what's happening in that now, which is lovely. Joke-based sorting algorithm that sorts a list by checking its order, it deletes half of the elements and repeat. So yeah, it does the thing I said. Concerning. What is this? Oh yeah, so it's just the thing. Yeah, so you can see the visualizer there that Kat put in chat, which is nice. Or just TikTok algorithm, TikTok search sorting algorithms that works as well, or Instagram or whatever your social media of choice is. But basically the gist of sorting algorithms is to put things in order. So the goal an unordered list into an ordered one. Typical orderings include numerical or like alphabetical. But basically something that has like a very clear structure. So maybe it's you're sorting dates, you know, earliest to latest, latest to earliest. Maybe you're sorting heights, smallest to biggest. And can be ascending, small to big, or descending, big to small. Which I feel like the vibe with like ascending alphabetical order is just like the order that you normally read it in, or the reverse of the order that you normally read it in. Yeah, years, a bit less obvious. But basically it's putting things in a structure, and then what's the optimal way to put those things in order. For example, like maybe it's sorting a deck of cards, right? Like K goes before, K goes after Q because king comes after queen in the deck of cards, but not in the alphabet. So having a really good idea of what you're trying to sort into is quite important for this. So with verbal sort, so you start by comparing adjacent items. In a list. And then if they are in order, leave them alone. If not in order, swap them. And then I feel like I'm missing a lot of steps here. Where's the formal definition gone? Oh, yeah, sorry, wrong thing. This was my sort of notes. And then the list is in order if a pass has no swaps. So that's sort of like the shorthand version. But obviously leaves a lot of questions. Going back to that conversation around like the cups of tea or the, you know, making a PB&J, if I said, go get a cup, you're like, right, we'll get a cup from where? So compare adjacent items, swap them. If they're in order, leave them a thing. It doesn't actually tell you sort of programmatically what step order to do things in, what steps to take, when to stop. What does a pass mean? That sort of thing. So the actual algorithm, as written by Pearson Edexcel, is number 1. Start at the beginning of the list. Working left to right. Which does beg the question, for people that read right to left, or for languages that read right to left, do they do their sorting algorithms backwards too? I wonder. Comparing adjacent pairs. This is where, if in order, leave as is. If not in order, swap. Part 2. When you get to the end of the list, when you get to the end, the last item will be in the correct position. And then it says this item is no longer in the list. And basically what that means is, like, if you're only checking over things, if I tell you that the last item is in the right place, you don't need to check it again. So that's quite nice. That it means that, like, the next time you go through things, and then this is the bit that I feel like should be added in. Getting to the end list is called a pass. So once you've sort of compared everything in the list once, getting to the end, the last item, that's called a pass, like one pass. Oh no. 3. If you have made swaps, go to 1. 4. When a pass is completed with no swaps, the list is in order. So, people are right to left implement the sort the same because we don't think of it as left to right or right to left. I think it's low index or high index, and write the sorts from low index to high index. Fair. We bubble sort, and we are indeed. So, let's have a look at the example of this that they give. So we can work through it. Sort into ascending order. So this is small to big. 24, 18, 37, 11, 15, and 30. So we start from the left-hand side and we work to the right. And I'm going to sort of overly dramatize. So I'm comparing these two numbers. Are they in order? Is the smaller one on the left? No. So what I'm going to do is I'm going to swap them. So I'm going to swap them. So I get 18, 24. And then I haven't done anything else to the rest of the list. So I do 37, 11, 15, 30. Okay. So I've swapped those, and now I look at the next pair of numbers. So looking at the next pair of numbers along, so the next two places, so index 2 and 3, I have 24 and 37. Are they in order? Yes. 24 is smaller than 37. 37 is bigger than 24. They're in the right order. So I leave them alone. 24, 37, 11, 15, and 30. Don't do anything there. Then I look at the next pair of numbers. I have 37 and 11. They need to be swapped. 18, 24, 11, 37, 15, 30. Moving down again, I have 37 and 15. Again, they need to be swapped. 15 is smaller, so it needs to go to the left. 18, 24, nope, 24, 11, 15, 37, and 30. And then finally, for this pass, we do 18, 24, 11, 15, 30, and 37. And this is just one pass. So first pass complete. So there's a lot of steps, but basically what you're doing is taking, if you have them in the order, so, you know, first entry, second entry, third entry, and so on, and their places, we look at the first and second, we look at the second and third, third and fourth, fourth and fifth, fifth and sixth, and you're sort of keeping it going. And what you'll notice that's happened here is if we just look at where we started, we have 24, 18. You know, the starting values were 24, 18, 37, 11, 15, and 30. And then at the end of the first pass, the numbers are 18, 24, 11, 15, 30, and 37. And what's happened is the bigger numbers have shifted to the right up till the next number bigger than it. So the reason that it's called bubble sort, I think, is that the big numbers float to the top, right? They float to the left. So you sort of one at a time take out the biggest part, and you get this like drifting of big numbers. So as 24 gets shifted up 1, but 37 gets shifted all the way to the end. And then the ones sort of in between, not too much happens because the biggest number is getting all of the attention. So, and the lower numbers bubble to the left. So the lower numbers do, but not like over time, yes, but it's more the action of the single bigger number moving, because maybe this isn't necessarily the best example, but like 11 and 15 aren't going to get swapped until quite late, because the 37 is sort of doing all of the heavy lifting, comparing things to the right. So if 11 and 15 were initially the other way around, it would only be quite late down the sort that they get. So yeah, things moving to the left only once at a time. Things moving to the right can move quite far. Yeah, so that's the vibe. So this was the end of the second pass. We can keep going from this point. So because we've already, the previous pass had things swapping, so this is first pass. So we can do it again. So we can look at the first and second entries, 18 and 24 are okay, so we can write 18 there. 24 is going to get swapped with 11. So we can write 11 in, and then we have 24 and 15. So 24 would be here next, but it's going to get swapped with the 15. So at the end of this pass, the 15 is going to be here. And then 24 would go here, compare it to 30. Yeah, no, it is smaller than 30, so we leave it alone. And then 30 gets left because we know that 37 is sort of done. And that's the end of the second pass. So doing it a bit quicker without having to write in sort of all of the steps, I did the exact same mechanism of sort of comparing, you know, as I did in orange here, place by place, but just checking like, okay, am I safe to write 24? No, not yet. I need to swap it. Am I safe to write 24? No, not yet. I need to swap it. So we can do the same thing again. So we now have 18 and 11. They're going to get swapped. So 11 is on the left. I would write 18 here, but I'm comparing 18 to 15. So I'm going to swap them. So I write 15. I would write 18 here, but I first compare it to 24. It's okay to be left alone. It's okay to be left alone, so that's fine. 24, 30, 37. So we know that the 30 and 37 were already all right. So now the 24 is good. So that is the end of the third pass. But we swapped things, remember? We swapped from the 18 with the 11 and the 15. So we do need to go again because we didn't have no swaps. So 11 compared to 15 is all right. 15 compared to 18 is all right. 18 compared to 24 is all right. 24 compared to 30. 30 compared to 37. So the third and fourth passes look identical, but the third pass had swaps in it. So fourth pass had no swaps. List is in order. One big reason we don't think in left to right or right to left is how numbers in programming work. 26 can be written binary or... Ooh, that's fun. I've never seen people write binary numbers the wrong way round. if that makes sense. Like, that's not a thing in maths as far as I'm aware. But computer programmers do their own thing, is what I've learned. Okay. Let's have a look. So let's have a look at doing... sorting the word networks into alphabetical order. So it's a little bit harder because alphabetical is not something that comes as naturally to compare as numerical order. For me, at the very least, I struggle to remember the order of the alphabet in quite a lot of detail. Like vibe, I know when things are like late alphabet, early alphabet, but like actual details, less so. But we're going to give it a go. Okay, so doing this in shorthand, comparing, and for some reason, I when I was writing this out myself, I was sort of putting my hand on, so I'd like leave my finger here until I was finished comparing, so I knew what I was comparing. So to put something into the first slot, we compare N and E. So E is earlier in the alphabet, so E goes there. Next, we're looking at what goes here. So we compare N with T. N is earlier in the alphabet than T, so we leave the N alone. Next, we look at this slot, T compared to W. T is earlier in the alphabet than W. Next, we look W compared to O. O is earlier, so we are swapping. So here we're comparing W with R. R is earlier. Next, we're comparing W with K. K is earlier. Comparing W with S. S is earlier, which means we leave the W alone. So that's our first pass. What up, Cat the Mathematical? Not much, Lufin. I hope you're doing well. We are doing some decision maths. We're learning bubble sort. It's late, I'm so tired. No, it's not because I'm shy. Go sleep. Honestly, I was gonna say it's an interesting hour to be awake. Go rest. We will see you in the next stream. Okay, second pass. So E compared to N. E is earlier in the alphabet. N compared to T. N is earlier in the alphabet. T compared to O. O is earlier in the alphabet. So now we're doing T compared to R. R, S, T. R is earlier in the alphabet. So the T here has sort of come this way and it's coming this way, so it's still going on. So T compared to K. K is earlier. S, T, T compared to S. S is earlier, so T gets left alone at the end. So, you know, we had one thing, like a big letter, a late letter was really early on and it's sort of bubbled its way all the way to the top, whereas everything else just got sort of shifted one at a time behind it. Doing it again, E compared to N, E is okay. N compared to O, N is okay. O compared to R, O is okay. R compared to K, now K gets swapped. And then we have R compared to S. P, Q, R. R stays where it is. And then S gets left alone. And I'm just writing in the end because, as we said, we don't need to check the very last entry because the biggest numbers are definitely going to the far right. So we need to, we can leave them alone. We know that they're there, that we know that that's done. You be rhyming. Are we writing sorting algorithm? We are learning bubble sort. And am I going to be looking at other sorting algorithms or complexity if it's in the Pearson EdXL Decision 1 or Decision 2 modules? For today, I think we're going to get to quick sort, and then I'm probably going to call it, and we'll do packing algorithms next week. But in the modules, as I'm learning it, it was decision maths with bubble sort and then quick sort. So I'll do one more example of bubble and then we'll move on to quick. Very exciting. You can read ahead. It's amazing. Okay, so doing the next one, E stays where it is. N compared to O stays where it is. O compared to K, K is lighter. O compared to R, L, M, N, O, P, Q, R. O stays where it is. R is fine. RST is the right order in the alphabet, so that's definitely fine. Nearly there. E compared to N, it stays where it is. N compared to K, K is finally earlier in the alphabet. N compared to O stays where it is. O, R, S, T, W. One more. E compared to K, E is earlier. K compared to N, K is earlier. N, O, R, S, T, W. Now there were no sorts, so that was second, third, fourth, fifth, sixth. No swaps on sixth pass in order. Ta-da! Quicksort is actually one of the most complicated ones. It's actually useful. I quite liked it. I'm going to be honest. I enjoyed learning it. I thought it was fun. What is chat's favorite in sorting algorithm? Let me know. Okay. Speaking of, let's shimmy our way over to quicksort. So called because I'm assuming it's quicker than bubble sort. Who knows? It'd be a really rogue choice if they only teach 2 sorting algorithms really early on, that the one called quicksort was slower. I'm just saying. Step 1, choose the midpoint or right of as the pivot. And when I was writing my notes for this stream, I was just shouting pivot in my head over and over and over again. Friends lives deep in my subconscious and I cannot get rid of it. Hey, look, it's... Hi, Starman. Pivot! Thank you. Thank you. I'm here all week. I'm not. I'm here for like another hour, maybe. Okay. Choose the midpoint or the pivot. Write down all items less than the pivot. Keeping order intact. Step 3, write down the pivot. Four, write down remaining items in order. Apply 1 to 4 to each sublist. Lists between pivots / ends. 6, when all items have been chosen as pivots, stop. Oh! We don't teach quick first. It's an optimized example of divide and conquer, and it's not only taught after bubble sort, selection sort. So this was taught second. So the order that I'm doing them in is how they were in the textbook that I am learning from. So it was bubble sort. It was like, here's what an algorithm is. Here's what a flowchart is. Bubble sort, quick sort, bin packing algorithms. Quite fun. Let's do an example. So I liked this one. I thought it made more like sense to me than the other one, than bubble sort. But I think that's because like you can draw it out more. So we can use the same list that we had for the first example of bubble sort, actually. I'm just going to copy all of that because I'm being lazy. Bum, 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 bum. Not too shabby. Okay. Okay, so it said to choose the middle item or the item to the right of the middle. So when you have an odd number of items, there is an item which is the midpoint. When you have an even number of items, you have sort of an even number on each side. So you pick the one to the right. So we have 1, 2, 3, 4, 5, 6. So we have 6 items. So we pick the one to the right to be our pivot. So I'm going to pick 11 as our pivot. So now we check through the list. So we compare 11 with 24 first. 11 is smaller, so ignore it. Compare it with 18. 11 is smaller, so ignore it. 37, we're looking for the values that are smaller than 11, of which there are none. Cool. So we have done step 2. We have written down all of the values that are smaller than 11. Done. So then we write down the pivot. Then we keep the list in order and write down all of the remaining numbers. So that is all of the numbers in this case. So we write down 24, then 18, then 37, 15, and 30. Now, between 24 and 30 is now our first sublist. The sublist that would exist to the left of 11 is non-existent. 11 was our smallest value. Nice. Then we take the middle value, and we take 37 in this case. This is quite a fun list to do this with, I'm going to be honest. And we write down, we compare numbers one at a time. So sorry, we write down 11 because that was from the previous one. And this is how I was doing, checking which was a current pivot and which was a previous one. So previous pivots are going to be in circles, current pivots are in squares. And we write down all of the numbers smaller, keeping them in order. So we compare 24 and 37. 24 is smaller, write it down. 18 and 37, 18 is smaller. 15 and 37, 15 is smaller. 30 is smaller. And then we get to the end of our sublist. So we write down 37. And now this was our old pivot, so we can ignore it. Our new sublist is 24, 18, 15, and 30. So taking the value to the right of the midpoint is now 15. 15 is the pivot of this sublist. So write down our old pivots. And then in this sublist, we're looking for values smaller than 15, of which there are none. So we write down 15, old pivot, and then everything else inside of that list becomes the new sublist. This one was actually a terrible example because normally there's multiple sublists that you need to sort through for a given line. So we'll do a more complicated example in a minute. So we write down our old pivots. So we take the pivot here is 18. 18 is the smallest value again. There are no things smaller. We have 24. And then 30. 30 becomes our new pivot. 11, 15, 18. 24 finally goes to the left, and then 30 is our old pivot. 37. 24 becomes the pivot because it's the midpoint of a list of size 1. And now everything has been a pivot. So the final list is 11, 15, 18, 24, 30, and 37, which is in order. Fantastic. What did I miss in chat? Why is Kat doing sorting algorithms? So decision maths is something that is taught at A levels in the UK. It is part of the maths qualification in parts of England at the very least, and maybe parts of Wales now, we don't know. It's not something that I did in school. So I'm trying to learn it now, basically. Okay, let's do a slightly more complicated list as a second example. So we've got 8, 3, 4, 6, 5, 7, and 2. Okay, so, and then we want these in ascending. Always good to have know what order we're actually trying to put things in. Bum, 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 bum. Thank you. It's fun. So if you remember the streaming anniversary that I did in May, I tried to sit a decision maths paper and I couldn't do it because I didn't know any decision maths. And it turns out sorting algorithms, sort of the thing you have to learn. Weird that. Okay, so again, using quicksort, we take our middle value, which here is 6, and we make that going to be our pivot. Then we go through the list and we write down everything that is smaller than 6 in the order that it is currently in. So 8 is bigger than 6, ignore it. 3 is smaller, 4 is smaller, 5 is smaller, 7 is bigger, 2 is smaller, and then we write down 6. And that was our old pivot. Then we leave the order that things are in for bigger. So 8 is bigger and then 7 is bigger. Now we have 2 sublists. So we do the sorting algorithm on both of these, which is where the distinction between current pivot and previous pivot is kind of useful. So the next pivot here in this list of 4 is going to be 5, and the pivot in the list of 2 is going to be 7. Do you cover median of 3? I have no idea. So I'm learning it, and then once I've learned a section, we're doing it. We'll find out. Okay, so in the sublist containing 3, 4, 5, and 2, 3 is smaller, 4 is smaller, and 2 is smaller. So 5 is bigger, so we write the pivot of our sublist, and then there's nothing bigger in our sublist, so that we write the next pivot. 7 and 8. 8 is bigger than 7, so we write up old pivot, and then we write 8. 8 becomes our new pivot. It's a pivot in a list of 1, so that's all nice and done. And then 4 is our middle value here. So writing down the values smaller, we have 3 is smaller, and then 2 is smaller. Then we write our pivot. Then we write all of our old pivots in. And then we write the old pivot from that one. And then finally, 2 becomes the new pivot. So 2 is smaller, 3, 4, 5, 6, 7, 8. And 3 is the only number that has not been a pivot yet. So they've all been chosen. We can stop. 2, 3, 4, 5, 6, 7, 8 is our final list, which is quite nice. There we go. We did it. Let's do... Okay, some facts about bubble sort, which I have lost my notes on. Do I have to do algorithmic complexity? I think it does come up, but it hasn't yet. Because I think we need to do packing algorithms first, if I remember the notes I wrote down. Yeah, but we can just mix them up, to be honest. So we can do that now. So orders of algorithms. Orders. So this was a really weird thing for me to try and learn because, like, I mean, it's been a hot minute since my first year of undergrad, but like learning the order of operations and like big O notation, little O notation, doing it sort of a bit softer. However, I am gonna write O of n and like O(n) squared and stuff using big O notation, and I'm basically going to I'm going to use the notation because it's quicker to write, but I know that that's not what they're being taught it here. So yeah, well, bear with me, basically. Like, forgive the abuse of notation that I'm doing. I know I'm doing it, but it just makes writing things a lot nicer. Do I think iteratively or do I think about the data set as a group? When I was just doing that, like sorting algorithms, it was iterative. Complexity is one thing to teach people and we get them to think about it. That's awesome. Nice. Okay. So the way that it's done for, you know, this is baby's first introduction to orders of algorithms. So everyone like bear with. The one thing that I find fascinating about how we teach maths in schools, at the very least in the UK, who knows where else, is it is very recursive. So when you're first introduced to a topic, it's sort of like fudged a teeny tiny bit. And then as you get sort of more and more down the rabbit hole, it becomes more and more clear. But for this exam and this board and this textbook at the very least, the order / complexity of an algorithm says how the change in size of the problem. So like think when we're talking about sorting lists, like the number of elements that we have to consider, or like basically the number of elements, the number of inputs, the size of the problem that we're trying to solve affects the time taken for completion, which is sometimes called runtime. Now, night, Lufin, have a good one. You can think of this in terms of going back to the beginning of the stream. We did happy algorithms, and it was sometimes like for some numbers, I mean, it was the same thing basically all of the time, but for some numbers it took like 2 steps, and then for some it took a really, really long time. We couldn't really understand a rhyme or reason to it, so we can't really comment on what the typical runtime of that is going to be. But when you have algorithms that are like really clear, like these sorting algorithms that are sort of very procedural, the main thing that's going to vary in that is the number of elements that we need to sort of sort through, right? If each time I look at 2 numbers and I use my brain and it takes me 0.1 of a second to figure out if this number is bigger than this number, the only thing that's going to make a difference is how many numbers I have to compare. So looking at 7 and 2, and that's my list. My list is 7 and 2. That's going to be really, really fast. Whereas if I have a list of 100 numbers that I have to sort through, doing whichever of these algorithms, they're going to take longer. But the question is how much longer, right? Because even just doing the bin sorting, the bubble sort versus the quick sort, we were doing different comparisons. Sometimes we were comparing more numbers than we were in other cases. If an algorithm has order f of n, then increasing the size of the problem from n to m will increase the runtime by a factor f of n over f of m. 3,000 numbers is a good quantity of number to show the difference. Fair enough. I'm not going to do a list of this by hand, but for computing and programming, it's definitely nice. And there's a whole thing of like, go on, no. We'd have to, maybe for a charity stream, I'll just do a really, really big bubble sort. A friend of mine did a 5-hour Tower of Hanoi algorithm, which was very impressive. Towers of Hanoi being this puzzle. If y'all have ever seen this. 1 second, nope, wrong button. That one. This thing is a Tower of Hanoi, and basically the game is to get the stack of discs from this side to this side, but you can only move one at a time. So like holding it with a hand and moving one at a time. And you can't put a bigger disc on top of a smaller disc. This is an illegal move. So to get the whole stack across, you have to sort of move them strategically so that you can sort of free up space to get smaller always on top of bigger. And there is an optimal algorithm to do this. And you can follow like a specific set of moves to get like the stack from here to here in the shortest number of steps possible. And there's a really nice tie that I cannot remember off the top of my head between doing this and binary digits. And I think it's something along the lines of, if this is, ooh, what is it? So it's 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. So basically, every time you move between them, you swap from a 0 to a 1. And if you list all of the numbers in binary, so in this case, it would sort of go up to a 3, like 1, 1, 1, you can sort of move them between. There's some really nice connection there, but basically there is an optimal solution to this that links to binary numbers in a really nice way. And then, so the recursion that you're talking about is if I only had, this was I saw this in South America and I had to get it. So, yeah, throwing things around. Right, this has only got 3 on them. The time that it would take to do this, I would repeat all of these steps and then add, if I added one more, and I had a 4 high tower, the time that it would take, like the steps are similar and the time it would take sort of increases, right? So every time I add a level, I'm adding an order of complexity. I'm changing how long it would take me because I have to do everything I did to get the 3 over, but I also have to get the big one over as well. And doing it by hand, so you can find, let me find Eliane's video, because she is absolutely iconic. So she was at a science festival. And she did a 14 high tower. On YouTube. Yeah, there we go. The algorithm is the same as, is self-similar. Yeah. So yeah, she solved a 14 high tower. So I have a 1, 2, 3, 4, 5, 6, 7. I have an 8 high here. But it was a very cool thing to do. But that's a nice algorithm. I really like these. They're fun puzzles. And yeah, as Lux was saying, I fell in love with them through Professor Layton. Between this and like having 3 jugs and, you know, they're like volumes 8, 5, and 3, and it asks you to put 4 liters and 4 liters in the jug. Like, I love those puzzles, and there's probably like some nice algorithms behind that as well. Ta-da! Do we classify those as scheduling algorithms? I don't know. I haven't learned scheduling algorithms yet. I'll find out and let you know. Okay, let's come back over here. So the one thing to keep in mind with this is that exact runtime will depend on the exact input, right? Okay, sorting a list of 3,000 is going to take a while, but if they're already in order, I only need to compare, you know, next entries once. So actually, a fully in order list, a bubble sort is the quickest compared to quicksort. Because in quicksort, we would still have to go through all the sublists and make every one a pivot. So, but for a really messed up list, maybe a bubble sort isn't particularly good. So For bubble sort, the number of comparisons is approximately, is this the maximum number or the average number? This is the maximum number of comparisons. So comparing everything to everything. So if you had a fully backwards list, you would have to sort of move each one up one at a time. So it would be the sum of n times, which is n minus 1 over 2. So say we took a list that was 5, 4, 3, 2, 1, for example, and we needed to bubble sort this, we would have to do 5 compared to 4. So 4, 5 compared to 3, which is 3, 5 compared to 2, which is 2, 5 compared to 1, which is 1, 5. And then we'd have to do this again. So we would, compare 4 to 3, 4 to 2, 4 to 1. 4, 5. But every time that we move one up, so here we had n comparisons, here we have n minus 1, we'd have n minus 2, n minus 3. And it would get fewer by 1 each time. So this is the worst case scenario, is like a fully reversed list. Does the study material talk about worst, best, general case? So the study material gave me this expression. And then I'm sort of like riffing around it. Let's leave that there. It does say, though, when considering order, it is best to use worst case scenarios. So in bubble sort, we had n times n minus 1 all over 2, which is n squared minus n over 2. So this has quadratic order. Right? As n gets really, really, really big, the thing that matters is the biggest power. And this is where first year undergrad comes in really, really handy, but oh well. So what we do is when we have a function in terms of the number of inputs, or the function in terms of n, the biggest thing matters. So n squared, n cubed, this is a linear order because it scales 1 to 1 with n. This is quadratic, cubic, quartic, quintic, and so on and so on. Okay. Yeah, we can do. Is there anything else in that bit? Otherwise, I'm going to chuck y'all on a quick break, and then we'll do bin packing algorithms, which was the one thing in the exam that I could do with no prep. It was just like fit these things in a bin. Don't know if I used the right sorting algorithm, but like, yeah, there were. It seemed to be the one that made the most sense. If your complexity has an exponent, it's probably not the solution you want. Yeah, the smaller the order, the better for like scaling with size. It's something that is very important when talking about coding or programming, is like, okay, it's all well and good to test it out on a small subset of values, but looking at bigger values, running a really, really complicated algorithm, or like we want to scale this up to, our full company operation if we're talking about, I don't know, some sort of algorithm that affects workflow or time or whatever. It's going to make a difference. So I'm going to chuck y'all over on a quick BRB screen, and then we're going to round up the stream with bin packing algorithms, or box packing algorithms, because I find the word bin weird in this case. I will see y'all in 25 minutes. I'm going to chuck an add-on, and yeah, see you soon. Hello. There we go. Much better. Have I lost my place? No. We're all good. We're back. I hope everyone's doing well. I hope y'all have had a stretch, had some water. And we're going to get started with bin packing algorithms. So in this section, it seems to be precisely you've got one-dimensional things that need fitting. I appreciate maybe volume is like three-dimensional, but you know, we're not worrying too much about anything too complicated. Just to get started with, again, I've got a feeling, like, I haven't read all of the textbook yet. I've got a feeling that it's going to get more complicated as it goes on. So maybe this is like a first introduction to. But we have bin packing algorithms. So this is a subclass, I can spell, subclass of problems with 3 algorithms we consider. So the ones that it makes us look at are fit first. I've just realized that doing dashes as points is a terrible idea when there's so many hyphens in this. So fit first algorithms, first fit decreasing algorithm, and full bin. And I'm hoping that these will make sense in a minute. Note that in this case, we define something called an optimal solution, where the optimal solution is one that can't be improved upon in this instance. That is any solution using the smallest number of bins. So bin packing algorithms are precisely what they sort of say on the tin. It's trying to put things into bins, into boxes, into groups. And solution is considered optimal when we use the fewest number of bins. If you think about me trying to like put books on the shelves, for example, if I can fit everything onto one shelf, that's great. If I just put one book per shelf, I'm going to use a lot of shelves and I'm going to have a lot of wasted space. But for an optimal solution, say I have 5 books and my shelves fit 5 books each, I fill it, sorry, no. If I have 10 books and my shelves fit 5 books each, I can put, say, 5 books here, and then 5 books here. And then both of my shelves are full. I've used the fewest number of shelves possible. But which 5 of those books are doesn't necessarily matter. So having 5 and 5 and then swapping them, that's also a different solution that is also optimal. So it doesn't necessarily matter which one is where. We don't really care about permutation in this case. The only thing that matters is the number of bins or the number of shelves in that example. We can determine a lower bound on number of bins needed, which indicates an optimal solution. So the lower bound in this instance being like, okay, if all of my books are, I don't know, 10 centimeters across or whatever the total width of book and then we take the total number of shelves plus remainder. It's going to be one more than how many it fits into. So I can write that out, hopefully in more coherent words. Lower bound is the number of bins if... What's the easiest way to say this? Is like the number of bins required for sort of the total amount of stuff divided evenly plus 1. So like, say the total length of my books was 20 and the width of the shelf was 18 in whatever units you so choose, I'm going to need 2 shelves is my optimal solution. Or is my lower bound on my optimal solutions. Maybe my one book is 20 centimeters long, at which point I think I'm scuppered. I don't really know how you do that. They don't really give you questions like that in... For your A levels, that's sort of too complicated, but it gives you some sort of indication of what to do. And we can look at an algorithm and then figure out how we work it out for that thing. So fit first algorithm is number 1, step 1. Take the items in the order given. And step 2, place items in the first available box. First available bin that can take it. Starting from bin 1 each time. So the good thing about this algorithm is that it's quick. I don't really have to think about doing anything. I don't have to do any pre-processing of my items. The downside is it's probably not a good solution. Right? Like I'm literally just taking a thing and being like, right, where's the first place that it will go? So let's do an example of that. So we're going to have the numbers 8, 7, 14, 9, 6, 9, 5, 15, 6, 7, and 8. And we have multiples. So these are actually labeled with A, B, C, D, E, F, G, H, I, J, and K. So we have elements that have size. They have some number attached to them into box bins of size 20. So the way that fit first works is we look at element A. We start with element A. Okay, and we put it in bin 1. Bin 1 is currently got 20 left, right? It's empty. 8 is less than 20. It can go in here. So we put A 8 inside of there. Now the space remaining, once we've put 8 inside of it, is 20 minus 8, so we have 12 left. Okay, inside bin 1. Then we look at the next element along, so we have this 7. So 7, starting from bin 1, can fit in here, so we add the 7 in here. 12 minus 7, so we are left with 5 inside bin 1. Hello, welcome in. We move down to the next item. So we're literally just going down the list, but we start from bit 1. And we only have 5. We have a space of value 5 left, and 14 is bigger than 5. So we then look at the next available bin, which is bin 2. In this, we're in control of how many bins there are. We've just gone and got, you know, another bin for this. But we're going to put C inside of there. So 14. Thank you for the follow. I'm doing good. We are learning decision maths. So in the UK A-level system from a few versions ago, back when I sat my exams, this was a module that I never took. I never learned myself. I'm a mathematician. I work at the University of Warwick as a mathematician. But I'm trying to learn some maths that we do at A-level in the UK. Seeing how it goes. So at the minute we're learning, similar to discrete maths. So at the minute we're doing algorithms. So we've done bubble sort and quick sort, and we're just finishing off with some bin packing algorithms. And we're just doing fit first. So we have bin 1 that has A8 and B7 in it. Bin 2's got C14. So in bin 2 we have space for 6 more items, size 6 left. So we look at the next one in line, and that's 9. Now that's not going to fit in either of the 2 bins that we had previously, so we need a 3rd bin. And we're going to put D inside of there. And that's going to leave me with 11 in that bin. Then we look at E. Now, bin 1 has 5, E isn't going to fit. Bin 2 has 6 left, so E is actually going to fit in that. And we're going to have 0 left. So bin 2 is full. All right, we have perfectly filled bin 2. Nothing else is going to go inside of that. So we can stop considering bin 2 in this system. Looking at the next element, F, doesn't fit inside bin 1. That's got 5. Does fit inside bin 2. That's got 11. So now we're left with a remainder 2 inside bin 3. G is going to beautifully fit inside bin 1. And now we have none left in that. So bin 1 and bin 2 are perfectly full, right? They add up to 20. They're done. Moving down the list, we have H, which is 15. That's not going to fit in bin 3, so we need a 4th bin with 5 remainder. Looking at 6, we have a space for size 2 in bin 3, a space for 5 in bin 4, so we're going to need another bin again. So I6, so that's going to have size 14 left. 7 is next, so it's not going to fit inside bin 4. It is going to fit inside bin 5. So J7, 14 minus 7, so we're going to have size 7 left. And then finally K8, it's not going to fit inside bin 4, and it's not going to sit inside bin 5. So we're actually going to need a 6th bin just for K8. So that's going to have size 12 left. So if we look at this, we've got 0 left. Let's do it in a different color so I can see it. If we look at how much wasted space there is, right? There's no remainder here. There's no remainder here. There's 2 left over in bin 3. There's 5 left over in bin 4. There's 7 left over in bin 5 and 12 left over in bin 6. So the wasted space was... So 0, 0 for the first 2 bins, looking pretty good, but then really quickly got quite bad. So we had 26 left over, right? That was a whole extra bin, more than a bin's worth of space wasted because we didn't do any sort of optimization of the problem. We just put things in the first available space that they went, which is really inefficient. So what can we do to fix that? Well, we can look at first fit decreasing. So in this one, sort the list into decreasing order, and then perform fit first, which is the algorithm we just did. So we sort them into biggest to smallest and then just put them in the next available space. And the idea behind this is that it is going to be a fairly good solution. But it might not be optimal. And then if we're doing this, properly and procedurally, the way we choose to do that sorting might take different time. So we're adding, runtime issues on top of optimization issues of storage space. So if we had like a really, really big list of numbers that we need to do fit first decreasing with, that's going to take a long time to do. And then, again, it might not give us the optimal solution. So using the same example, I'm going to write the numbers big, the letters big at this point. So we have A8, B7, C14, D9, E6, F9, G5, H15. I will say the one thing I don't like about decision maths is like how much writing there is that I need to sort of do on the top. I6, J7, and K8. Okay, so this is our list. But now we need to put it in descending order of size. So the decreasing size order. Remember, the A, B, C, D, E is just for the labeling because things are of the same size. So if we're going to do this, we would have H15. I'm not going to perform a sorting algorithm to do this, but we could. 14, D9, F9, K8, A8, J7, B7, E6, I6, and then G5. So now they're in biggest to smallest. And now if we do the fit first algorithm, so we go down this list and we put them into bins. So we start with bin 1, and that's going to have H with 15, and that's going to have space 5 left over. And then we do C14. Now that's definitely not going to go in the first bin, so that's going to get its own bin. 14 with remainder 6. And it's kind of like a common trend. Basically what you're doing is you're putting the biggest thing in its own bins first until you can start doubling up. So D9, remainder 11. And now finally we can put F9 in here, which is sort of basically what we had before, right? That was actually the same as the fit first one. Bin 4 then gets K8 with remainder 12. A is now also going to go in here with remainder 4. Bin 5 is going to get J7. J7 with remainder 14. It's going to get B7 with remainder 6. Sorry, remainder 13 even. 13, 7, 6. And then we look at E6. Now E6 can go up here, remainder 0. I6 can come down here and go remainder 0 again, and then G5, remainder 0. So now if we add up the remainders of what sort of wasted space we have, there's no space there, there's no space there, there's 2, there's 4, and there's no space. So there's only 6 wasted space, which is much better than 26. That's a whole bin's worth extra, which is quite good. Okay, and then last but definitely not least, sorry, just getting a bit warm in here. We have full bin packing. Okay, so full bin is similar to fit first decreasing, but we do even more sneaky maneuvers before we sort of start doing it. This is all like pre-processing behavior, basically. Like the whole thing is put the thing in a box, but get yourself in the best position possible to put things in boxes is the vibe. So here is use observation to find combinations that will fully fill a bin. Pack full bins first. And then use fit first. On remainder. Okay. So this, again, usually is a good solution. But the downside is it is difficult for large numbers. Or like really awkward numbers. Say I tell you that you've got things that are, you know, really complicated numbers. You've got a lot of measurements all between 0 and 1, and you've got to put them in boxes. It's not super like intuitive what's going on. Is it still with alchemists when packing their grocery items in the self-checkout? So, I think so. Like you want to put the heavy stuff right at the bottom of the bags first because you don't want to put heavy on top of light, which is sort of different to this, but maybe the big stuff in first and then you can fit around it. There's a really nice way of doing it of like how much stuff you can fit in a space. And if you put small things, like say you pour sand in and then you put ping pong balls on top or something, you can fill less than you can if you put the other way around. Comp sci algorithms course. Yeah. Well, welcome to the maths version. So, same example again. Let's just keep using the same values. Okay. So here, like we can use the fact we've done this twice already is quite nice, but we can use that C14 and E6 are equal to 20. We can use that J7 and B7 and I6 are equal to 20. We can use that H15 and G5 are equals to 20. So that gives us 3 bins. And then there's nothing really we can do with the 9s and the 5s. But we would do bin 1 is H15 G5. Bin 2 is C14 E6. Bin 3 is J7 B7 and I6. And then bin 4, we would have to just do fit first. So we'd have D9, F9, and bin 5 would be A8, A8. So the wasted space here is 0, 0, 0, 2, and 4. So it's 6 again, which is the same as fit first decreasing. But the question is, could we have done better? So the way that we work out our lower bound is the total value of the items, right? If we add up, so A8, B7, whatever, we would get, I can do it quickly here. So I have 20, 40, 60, 60 at 9 at 9, at 8 at 8 is 94. Right? So 94 divided by 20. Say we fully fit as many bins as possible. Is precisely 4.7. Okay, so 4 full bins with remainder, plus 1 from the remainder. So the lower bound is 5 bins. They physically cannot fit into 4 bins. There's too much stuff there. If this had been an integer, if it had been like 5 bins exactly, if they actually fit 5 bins exactly, then it's sort of like, okay, well, that tells you that it's going to be 5 or 6 bins, depending on the size of the objects, whether or not they all beautifully fill the bins. But we're doing pretty good, right? We had 5 bins for the fit first decreasing, and we had 5 bins for the full bin packing. We had 6 bins just for fit first. So fit first is easy, it's quick. It is not the most efficient way of doing it, right? This took 6 bins because we had like this massive wasted space that we could have optimized and we didn't. So that is, I think, all of chapter 1 of the Decision Maths course, which is very exciting. There's a load of additional questions that exist inside of it, but I think I'm going to save that until the end of sort of the module, and then we can have a look at sort of exam style stuff.